Hi everyone! This lesson is going to be on bonds. The first topic in this lesson is on types of bonds, where we will learn what bonding is and the difference between ionic and covalent bonds. The next topic will be on polarity, where we will discuss what it means for a molecule to be polar and how that relates to electronegativity. Then we will talk about Lewis dot structures, where we will learn how to visualize where an electron is on an atom. The final topic is on molecular structures, where we will talk about the appearance of molecules and use our newfound skill of visualizing atoms to visualize molecules. Hi everyone, my name is Caitlin, and I'm going to be talking to you about types of bonds. So to start, what is a bond? A bond is a joining of two or more atoms. This usually comes from sharing or trading electrons. A bond can be strong if it's really hard to break apart, or super weak if it's easily broken apart. The bonding of an atom usually leads to these atoms traveling together because, like I said, they are either sharing or trading electrons, so they need to stay together. Once they stabilize, they have strength and they don't want to separate. All right, so what are the types of bonds? There are lots of types of bonds, but two of the main types are ionic bonds and covalent bonds. Ionic bonds bond together by transferring electrons from one atom to another. They do this so that the covalent shells, or the outermost shells of the atoms, can be full. And once the outermost shells of the atoms are full, these atoms become stable, and all atoms want to become stable. Now, covalent bonds are a little different. Covalent bonds share electrons in order to fill their valence shells. With the sharing of electrons, each atom has the electron in their valence shell. So sometimes the atoms evenly share the electron, each pulling equally on it. And other times, one atom pulls harder on the electron than the other. When they're evenly shared, this is called a polar bond. But when they're unevenly shared, it's called a nonpolar bond. So we need different types of bonds because each bond provides different properties to the molecules. For example, the density of a molecule, the solubility of a molecule, or the conductivity of a molecule. We need all these different types of bonds because if we didn't, we wouldn't have varying properties in any of our materials, our objects, or in our life in general.
Hello, my name is Grace from Massachusetts, and today I'll be talking about electronegativity. The definition of electronegativity is as follows: the tendency of an element to attract shared electrons when forming a bond with another atom. Electronegativity is a property that is intrinsic to the specific elements in the periodic table, and it is, in fact, considered to be a periodic trend. We know that electronegativity tends to increase as we move further to the right in the periodic table. Some notoriously electronegative elements are fluorine, oxygen, and nitrogen, in decreasing order of electronegativity. Electronegativity is measurable through some scales and has specific values for each element. Now we'll be talking about polarity and its relationship with electronegativity. So as we just saw in the previous slide, electronegativity is a tendency to attract the electronic density that comprises a covalent bond. When such things happen to a certain extent, it can be said that a molecule is polar, meaning that the electronic density is significantly concentrated around one of the ends of a covalent bond. For a bond to be considered polar, the difference in electronegativity between the atoms at each end of the bond has to be less than 4/10, or 0.4. That is the lesson on electronegativity for today. Thank you for listening, and I hope this was helpful. Hello, my name is Grace from Massachusetts, and today we'll be talking about the dipole moment. The two differentiated regions of a bond, one of them electronically dense, are referred to as dipoles. Said regions have electrically opposite charges. For a molecule to be considered polar, two conditions must be met. Number one, there must be at least one polar bond. Number two, there must be an overall dipole moment, meaning that the spatial organization of atoms in the molecule must not cancel out the vectors that result from the electrically differentiated regions. A molecule that does not meet these two conditions is considered apolar. Now we'll talk about the graphic representation of dipoles. Dipoles can be represented by the Greek letter delta, followed by a minus sign to distinguish the negatively charged, also known as electronically dense, region around the atom of greater electronegativity, and by the letter delta and a plus sign to signalize the positively charged, non-electronically dense region of the bond, as shown in the picture here. That is our lesson for today. Thank you for listening. Hello, my name is Grace from Massachusetts, and today we'll be talking about Lewis dot structures. The purpose of Lewis dot structures is to help us understand why certain elements will react or bond with others based on the number of electrons they hold in their valence shells. An element will have a certain number of energy levels depending on how many electrons it has. The first energy level of any element can only hold 2 electrons. If that is full, electrons will begin to fill subsequent energy levels. Each level, except the first, will be able to hold 8 electrons. Lewis dot structures only display electrons that are in the element's valence shell because the reactivity of an element is based on the number of valence electrons. In short, Lewis dot structures are diagrams that allow us to visualize the placement of valence electrons in atoms and molecules. Now, how do we figure out how many valence electrons there are? In order to draw a Lewis dot structure for a single atom, we must first determine how many electrons are in each valence shell based on its group. So group 1 to 2 have the number of valence electrons that correspond to their group number, and we can look to the periodic table for this. Then groups 3 to 12, the green and the purple, do not follow specific rules, so they'll need to be researched independently. And then 13 through 18 require some simple math and subtraction. Take the number of the group and subtract by 10, you'll be left with the number of valence electrons. For example, group 13 has 3 because 13 minus 10 is 3, and group 17 has 7 because 17 minus 10 equals 7. The exception to this is helium, because even though it's group 18, it has 2 valence electrons. It is a stable element because the 2 electrons fill its 1 energy level. And helium is in the top right of the periodic table. Now, here we can use a carbon atom to practice. So the carbon atomic number is 6, as we can see right here on the periodic table, so it has 6 electrons. 2 of these electrons are filling the first energy level. The remaining, as we can see here at the C at the top, the remaining 4 electrons are in the second energy level, the valence shell, as shown in this picture down below. Each atom's goal is to have a full valence shell containing 8 electrons. This can be achieved by 2 methods, giving or gaining. The carbon atom has 4 valence electrons, so it wants to bond with an atom which also has 4 valence electrons, or bond with multiple atoms whose combined valence electrons equal 4. Or the carbon will lend its electrons to other atoms. So right here, for example, in this bottom image with the red and the black, oxygen has 6 valence electrons, where 2 oxygen atoms bond to carbon. They each borrow 2 valence electrons. So that's why the C and the O are connected with the dots. These bonds will fill the valence shell for all the atoms involved and create a stable molecule. If the electrons are being shared between 2 atoms in a molecule, the dots that symbolize the electrons will sometimes be replaced with a line. As you can see in this image here, where there are the dots that are being shared, that could be a line instead. Thank you for listening to this. I hope it was helpful. Goodbye. Hi, my name is Grace and I'm from Massachusetts. Now that we've covered our lesson on Lewis dot structures and we've discussed the different amounts of electrons around a nucleus, let's apply these concepts that we've learned to real life. So let's use the example of magnets. Negative and positive ends attract each other, but two positives repel each other. Same with two negatives. Two negatives repel each other. This same concept applies to molecules, given that different atoms have different charges. So, as we'll learn in the next lesson, some elements are better at taking electrons than others. So this means that within a molecule, some atoms will be a bit negative and others a bit positive, depending on how the atoms are sharing the electrons. Because the negatively charged atoms wants to be far away from the negatively charged atoms, and the positively charged atoms want to be far away from the other positively charged atoms. Again, just like this magnet example that we have, the negatives repel and the positives repel. This means that molecular shapes can end up looking pretty interesting. So let's draw them. Here's how you can draw molecular structures. So use the steps that you learned with the Lewis dot structure earlier, and then count the number of electron pairs around the centrum atom. Arrange these pairs as far away from each other as you possibly can. And then here's the table for the structure. So they can be linear, with just like one pair on either side as far away from each other. There's a triagonal pair, planar, excuse my pronunciation, tetrahedral. Again, you can see the four parts far away from each other. And then there's other structures for 5 electron pairs and 6 electron pairs. If there's any questions, please let us know. That is all for now. Thank you.